Well, good, good evening, everyone. Hopefully you are listening to me in good conditions. And today the tutorial it's about software that somehow I'm a kind of a creator of this myGeoffice.org. So this is a web platform for geographical information systems, in particular for people that somehow are interested in following very much the area of special statistics. So somehow the capability in order to produce results that somehow have a statistical point of view, very much associated, of course, with probabilities in terms of the results. But the major difference definitely it doesn't follow very much the traditional, let's suppose, softwares like the SPSS or R softwares, where very much we have sometimes under the statistics, as you know, I suppose a kind of a son of the math science, the concept of probability between zeros and one, everything is so fine. I suppose working also with the special statistics. But the major difference, I believe, is the capability also to handle special data. So special data somehow is very special, all right? On the concept that many of the rules that somehow imposed by Mother Nature is not probably the same ones as I suppose statisticians most of the times they follow. If you still remember from probably your previous classes of statistics and also probably several years ago, if you are not already handling, very much in terms of these kind of types of an analysis, we have several, let's suppose, basic conditions. One of the conditions, for instance, is, let's say, the independency of the facts. Okay, so whatever you're trying to study, one fact is independent of each other. So this always brings that kind of concept of the degrees of freedom associated, let's suppose, to the study that you're doing. And the more samples, of course, the more the degrees of freedom, and definitely all those kind of tests that we use to do it. So most of the times, it's very much related, let's suppose, on the quantity of information that I have. Using special data, first of all, we have very much associated with the location. This location could be two dimensions, X and Y, it could be X and Y and Z, three dimensions, which is somehow the world that we're living. And if we had, let's suppose, a time factor, just a little bit like Albert Einstein did it on his theory of relativity in 1905, space and time, they are somehow very much intercorrelated, okay? So one of the basic rules that definitely special data doesn't follow is that let's suppose independency of the facts, independent of the sample. So quite often this is very much broken, let's say, by the sometimes known as the first law of geography, sometimes known as the Tobler's law of geography, first law of Tobler's law of geography. Sorry. And basically, it just says that everything else is related with everything, but the closer things are more related than far away ones. Somehow, it seems a little bit kind of trivial, but this particular sentence definitely, is going to put very much, let's suppose, in question, let's suppose the independency of facts that definitely statistics, most of the time it follows. Just to remember, statistics itself, quite often we have descriptive statistics, we have Bayesian statistics, then we have also the field of probabilities, and then we have what we call univariate statistics, and then also we have multivariate statistics. Okay, so most of the time, let's suppose, the major areas that somehow this particular field. Special statistics, it's a particular field of geographic information systems. So GIS tried to handle, let's suppose, this space component, because when we have, let's suppose, the location, let's suppose, of customers, of suppliers, of clients, of co-workers, of companies, of disease, of pollution factors, whatever it is, there's a space associated with that. But probably you never notice that this particular data has somehow information inside of it. The question here is how can we extract, let's suppose, that particular information? So that's where, let's suppose, GIS comes along. It's an area that somehow was born probably during the 1960s, 1970s. Definitely now, somehow in terms of software, I consider Jack Benchermon, let's suppose the CEO of Israel, the biggest player, let's suppose in terms of GIS. He was the one, let's suppose, he was a kind of fanatic of the geography itself. So basically, he was the first one making the first steps in terms of software for this particular, let's suppose, area of science, in particular computer science itself. So the purpose of this is the using of myGeoffice. So just like probably saw some of the slides that I mentioned before, we have different types of solutions, very much independent softwares. We have also extension of the typical statistical softwares, like R with special extensions to handle this. And myGeoffice comes, let's suppose, on the advent of the internet. So the internet is father, Tim Berners-Lee. Basically, he set it up, let's suppose, this kind of concept, the HTTP protocol back in 1992. And somehow the internet is a disruptive technology for organizations, NGOs, business, governments, and also, of course, for people in personal life. And definitely now myGeoffice try to bring, let's suppose, this software as a service, sometimes known as a Web 2.0 tools. So bringing, let's suppose, you don't have to download any software, you don't have to install it according to the different types of operating systems. Basically, you just need to run, let's suppose, the software from the web, and that's it. Okay, so that's very much, it doesn't matter where is the software. It's somehow we call this the ubiquity concept. So 24/7 and whatever, everywhere, every time. So mygeoffice.org, also like I mentioned already before, it's a project that started, let's say, with my PhD thesis. Its first name was SAC-Web, Special Application Creating Web. And then it was developed, let's suppose, on a postdoc that somehow I did it back in University of Maria and Andalusia, back in Spain. So that's a little bit, a little bit of the story. And then finally, this was finished back in Macau. I lived there for 9 years, Macau, China. And I also have, let's say, some kind of scholarship also from the FECT of the, let's suppose, of the local authorities in order to finish. And those are the ones that somehow support, let's suppose, the web server that is running at this moment at the University of St. Joseph back in Macau. So the purpose of this is try to show you a little bit about myGeoffice and its capabilities. So once again, you just need to type mygeoffice.org. And this is a domain name that has been already bought for several years. And this is very much a little bit what I like to show you during this particular tutorial, okay? So once again, if you click it here, basically, the web browser somehow is, let's suppose, the graphical user interface of this software somehow. So all of these are options that you have here. So basically, this myGeoffice is divided, let's suppose, into two different menus. So we have, let's suppose, this menu. I call this kind of menu a little bit about a special interpolation. So somehow this is a process, okay? So basically this process starts from the left to right, the top to bottom. So somehow you're going to start doing all these options, then all these options, then all these options, okay? And also all of this, and then we have also the final ones, this one. Okay, so somehow this is a process itself, okay? And the purpose here is, if I have a set of samples, I want to know what's going on where I don't have the samples. So somehow I wanted to generate some kind of a map that somehow it can tell me, what are, let's suppose, my best estimation, for things that I don't know. Quite often, this particular process, as you're going to see later, it's very much associated, let's suppose, for pollution problems. Okay, so most of the times, if you go, let's suppose, to them, you pick up several samples in order to figure out, let's suppose, the levels of toxicity or any kind of damage. And most of the time, then you wanted to figure out, okay, what happens, let's suppose, through the whole space of that particular dam. Okay, the same happens, let's suppose, with temperatures. Most of the times, when you look at the temperature, let's suppose, of any particular city, there are samples, in different types of quantities. So basically, somehow when we figure out, let's suppose, that the whole plume of the, let's suppose, of the city in terms of the temperature, in terms of the humidity, in terms of raining levels, and in everything, everything is based on samples, because definitely it's not possible to have in every point, trying to make measures of any particular substance that we try to move forward. So this is very much the area, let's suppose, of what we call spatial interpolation. This one, the first one, is a little bit different. So somehow all of this, I used to call these functions, so somehow a function, if you calculate it, let's suppose a tier, you have a certain type of variable, a certain type of, let's suppose, purpose, in this case, the ordinary squares or bivariate regression model that probably you have learned through your basic statistical classes, and then you try to estimate something. Okay, so that's most of the time what you have, and that's basically it. So somehow there's a kind of independency, let's suppose, between all these options or among themselves. So somehow there is no relationship, let's suppose, of all these options, which is something that it doesn't happen, let's suppose, here on these particular cases. Okay, so this is certainly, a big difference between, let's suppose, one menu and another menu. The purpose of this tutorial, like I already mentioned, it's try to figure out, what's going on with this particular software, and try to see if probably if you have some kind of interest, try to learn, some of the things that probably can be interesting for your own particular studies. It's quite common, at least I found that in particular when I talk already with colleagues of mine, many times they have the location, they have the space, let's suppose, of the different types of variables they're trying to study, even if they are, let's suppose, studying, let's suppose, patients, let's suppose that exists inside of an hospital, or customers inside of a shopping mall, or very much sometimes known, let's suppose, using sensors, using big data, and associated, let's suppose, to the management of cities. Okay, so whatever it is, we have location. So once again, here is, does the location also somehow helps to explain what we're trying to look forward? So somehow this is where special statistics comes along. Okay, and try, of course, to respect this kind of special dependency, somehow enunciated by Tobler's law, the first law of geography. So let me just try to take a small look. I'm not going probably to very much into detail. It's not also the purpose of this, just for probably more, at least on the first level, probably some kind of curiosity. I believe that the majority of the listeners probably are not very familiar with all these kind of concepts and those kind of concepts. So if I go here, let's suppose, to the keywords, all of these are part of what I call the jargon words, of this particular science. Okay, so probably if you look at them, many of you are a little bit, wow, I never even probably expected that all these kind of words really exist. And somehow probably you already heard about some of them, but probably your knowledge or probably never use it for yourself. So somehow this is a little bit about the real world of special statistics. So somehow, of course, we have here also other words that, of course, is also maybe a little bit related with information technology, okay? But the majority of that, it's very much associated to words that somehow are very much, let's suppose, geographic information systems, buzzwords, okay? So that's a little bit about the word. And for you, if you want to understand this, I'm sure all these kind of words, somehow are familiar to you. So we have here also other ones. One of the things that definitely, myGeoffice has already been restricted with the Java platform. So once again, all this software was set up on an Internet Information Service. We're talking about Microsoft technologies. We're talking about lots of operating system, in particular IP service pages and IP service pages 2.0. Somehow a kind of a VB script language, that somehow is processed on a runtime. All right. There's also code that comes particularly from Fortran language, Fortran 77 and Fortran 90, and also from C language. Okay, so somehow these are some of the language that exists behind this. Of course, in order to run this, we need also some other technologies, in particular hypertext markup language, HTML. Also, some JavaScript has been already used. Some of the programs, in particular, to call, let's suppose, executable files, we have, let's suppose, even PHP also running as well. But somehow we have, let's suppose, on the background, on the main server, we have Windows Server, I believe, the version 2016, I believe. I'm not completely sure about which version is it. So once again, if you go over here, we have a lot of, let's suppose, possibilities. I don't know, let's suppose here a glossary. So somehow very much associated to words that somehow it's very much GIS concepts. Okay, so all of this, for the people that somehow are, let's suppose, closely friendly, with this particular science, I'm sure, these kind of concepts are familiar to all of you. All right. So somehow it's a kind of a glossary just for people that somehow probably has, some kind of knowledge on this particular field. Other capabilities, of course, I'm not going to all of them here, exploratory exercises. These are some exercises of some students of mine that they did it when I taught in Macau. I left Macau around 2 years and a half. At this moment, I'm here at the Zayed University in Abu Dhabi, UAE, United Arab Emirates. Okay, so a kind of 150 kilometers of the big city of Dubai. Nevertheless, Abu Dhabi, believe me or not, it's the capital of the UAE. Okay, so around 80%, let's suppose, of the UAE belongs to the Abu Dhabi state. In fact, these are 7 states. Sharjah, Dubai, Fujairah, and probably some other ones that I don't know already the name. Because truly speaking, I've never been on those ones. All right, but all of them are kind of big, basically the state somehow is a small city. Basically what it is, because somehow 80% represent Abu Dhabi. So here, let's suppose even a call of Google Maps. I'm a very fan of Google itself. So once again, can also probably do something like this. And definitely, this is, let's suppose the birth and where is, let's suppose, the software running. So as you know, Macau, it was kind of an old colony under the administration of the Portuguese since the 16th century. And back in 1999, on the 20th of December 1999, it was the handover. 2 years before, it was the handover of Hong Kong. Okay, so somehow Hong Kong, it's somehow about, I don't know, 1 hour from jet fuel from one to another. But at this moment, it's part already of China, of the Guangdong area. So I'm sure, you already heard about these kind of stories. And once again, we have also here, in terms of Java, I'm just talking this because I put here the Java capabilities because all the options that I have here in terms of the raster image processing are, let's suppose, web editors using Java, whose capability was to enhance, I suppose, the pictures that somehow are the maps that are produced by all the other options. Okay. At this moment, as you know, Java applet is not already running. I believe the only browser that is still running is Internet Explorer. But if you go, let's suppose, to other, let's suppose, browsers, I have here several ones, as you might see here. Microsoft Edge, Firefox, Safari, none of them they work in Google Chrome, which is the one that is at this moment my preference that I'm running. So only on Internet Explorer, I believe, still this runs. Okay, all these options, but once again, it's part of the game. Some of the technologies they come, and some of the technologies they go. Java level is already gone. So once again, everything is very much accomplished, I suppose, by let's say JavaScript. So here others information. Okay, there was even a book that has been already, let's suppose, published by EG Global. So once again, if you want to know some information, just can forward click it here. Okay, so once again, it's about special techniques, special analysis techniques using myGeoffice. Okay, so that's very much a little bit about the story, let's suppose, also that behind this particular software. All right. Some other, let's suppose, information, let's suppose user guides credits. So somehow this is, let's suppose, the time zone of Macau, and in fact, all China, okay, they have only one single time zone, completely different from the pros, let's suppose, from Russia. Russia has 7 time zones, okay, although, of course, Russia is the biggest country in terms of size of the world, okay, so definitely not, but a different perspective. So I have here some notes, some of the things that you really might find it maybe interesting for you to check it later on. Okay, this is the web server location. So somehow, or when you connect it to myGeoffice, you might have an idea where it's located. So this is basically, once again, the location. Although my location, or present location, is somewhere around here. Okay, so somehow the UAE. So we're talking about around, I don't know, 6 hours flight between Macau and Abu Dhabi, more and less. Okay, so just a reference number. And then, of course, you can also do zoom in, you can also do zoom out, So once again, the typical capabilities that we always do using maps. We have also here a mind map. Mind maps, I think it's very useful. I'm a very visual learner, so somehow, it can tell me, in a very much graphical user perspective, how the things are somehow structured. What is the model that lies behind? So once again, myGeoffice, we have the first main menu, so very much associated to raster pointing function. So, and here we have all the functions that somehow are very much interconnected. On the second main menu, it's very much associated to special interpolation and simulation. So somehow all of these are the options that you're going to find that let's suppose associated, let's suppose, to this particular software. Okay, so once again, feel free always to look at it. And once again, if you never saw, let's suppose, this kind of content, once again, just a kind of an introductory level, just what are the things that we really can do at this moment, I suppose, special data. Okay, so many times on your analysis, whatever it is, the field that you're looking forward, many times probably you have the location of that particular event, of that particular thing, whatever it is, things means here, In particular, now that we're talking about Internet of Things. So whatever it is, Internet of Things, of course, is very much attached to networking, very much attached to security, it's very much attached, putting objects talking with another object. Of course, also very much attached to sensors, but all of them, they have a location. So somehow the location, probably is also another component that somehow we can extract information from that particular data. Okay, so that's a little bit, where we are. So let me start on this a little bit, just some of the options. I'm not going to do all of them. I don't want to be exhausted. Okay, it's not to the purpose. Okay. So this is, let's suppose, one of the functions we have here. Let's suppose what we call the Dijkstra, let's suppose, shortest path. Dijkstra was, let's suppose, a gentleman, I believe, from the Netherlands during 1950s, 1960s. He was a kind of a computer engineering, and basically he set it up one of the most famous, algorithms in order to connect, let's suppose, the shortcut path between several points. Okay, so if I have one point A and I want to go to point B, and I have so many options between A and B, most of the time this is the algorithm that is being used. In fact, this algorithm is using for routing or OSPF, which is Open Short Path First. It's an algorithm, let's suppose, used inside of the internet in order to figure out, let's suppose, what is the shortest path between my computer and, let's suppose, myGeoffice.org. So this goes to the internet. We have so many different routes inside of this. So somehow this tick somehow helps in order to figure out what is the best way in order to reach that. Of course, this best way is everything is always much based. What is the cost? What is the level of cost? Are we talking about money? Are we talking about distance? Are we talking about time? Are we talking about any other type of cost? So somehow it's always trying to minimize those costs. Okay. I'm sure if you have, let's suppose, a kind of a brand new car that have, let's suppose, GPS and mapping, and you ask, let's suppose, according to your location, and I want to go to a specific point B, most of the times, the system tells, okay, follow this route, do this roundabout, go straight, cross the bridge, make a left, and then turn right. Okay, this is also the Dijkstra running behind that. So somehow this is definitely, a special, function that somehow it can be important. All right. So let me go back here once again. My GeoOffice, Dijkstra shortest path. So somehow in all of the examples that you will find that, let's suppose, and we have always, let's suppose, a data set sample. Okay. So once again, the purpose is just probably just to run it for you to, if you want to have, this kind of small experience, and at least for you to know, what's going on behind, let's suppose, in terms of the algorithm. So somehow this is a free web platform, so you can use it whenever you want. There's nothing here to pay. You don't have to register. You don't have to give any emails. Nothing. Okay, so that's very much a little bit about, and it's very much open. Okay, I strongly believe very much on this kind of concept. It should be open and not asking for, a specific personal information regarding that. So I have here, let's suppose, imagine, let's suppose this example, let's suppose I did, let's suppose, a snapshot, or let's suppose this is the Dijkstra using, let's suppose, data from Brazil. So Brazil is a huge country in South America. So once again, these are, let's suppose, the cities, let's suppose, of Brazil. But in fact, I'm sorry, this is about something, there you go. These are the distance that I have it. I'm sorry. Okay, just a small error. I thought it was the minimum spanning tree. So somehow I have all these cities, Recife, São Salvador, Ribeirão Preto, Rio de Janeiro, Porto Alegre, Goiânia, Belém, and Manaus. Okay, and of course there are distances among them. So imagine, let's suppose, I want to travel, let's suppose, from one point to another, or from this point to another point, and so on and so on. So all of these are distance. Okay. So the purpose here is how can I connect from one point to another on the shortest way? Okay. So that's a little bit about the case that I'm trying to put it. So if you look, let's suppose, at the file, somehow I have here a kind of a matrix. Okay, so somehow the distance from point 1 to point 2 is, let's suppose, 112, I don't know, let's suppose, hours or minutes, whatever it is a cost. The distance from point 1 to point 3, from 1 to point 4, and so on and so on. So I have here, let's suppose, the cost between point A and point B. Okay, whatever it is the cost means to you. All right. So the purpose is basically somehow a kind of a very user friendly. So let me just go back here to the directory of downloads. I'm sorry. Let me just probably put something like this, a little bit like this, and let's figure out here Brazil Dijkstra. Okay, so once again, I do the upload. Okay, and then there will be, some kind of, running in this page, as you can see here, active service pages. Once again, press here for the Dijkstra J on computation, some kind of. So once again, what I'm trying to say here is, if I want to connect from node 1 to vertex number 2, the best way is just go to 1 to 2, and the cost of this is 112. If you want to go to node from 1 to node number 3, you've got to go also direct from 1 to 3, and this is the cost. From 1 to 4, basically, once again, you go to 1 to 4 directly. Well, let's suppose if I want to go to travel from node 1 to vertex number 6. So the best way here is first you go to number 5, and then you go to number 6. If I want to connect, let's suppose, from node 1 to vertex number 8, the total cost is 518 units, and first from node 1, you need to go to node 2, and from node 2, you need to go to node 8. So, of course, here, this kind of nodes, somehow is very much represented, let's suppose, by this particular image. Okay, so I'm just considering here, let's say that this is node 1. So basically, my location is Ribeirão Preto. I want to know, what is let's suppose, the best way. Of course, this is a very simple case, okay, because once again, myGeoffice, or the purpose of myGeoffice, is simpler education, okay? It's just for us to learn, how the things work and what are the types of algorithms that we can have. Of course, you can make, let's suppose this connection a little bit more probably complicated, okay? So let me see here, let's suppose this Dijkstra from India. So There you go. So I have here, let's suppose, these locations has coordinates, okay? And I wanted to figure out, let's suppose, how can I go, let's suppose, from, I believe, point number one to the other ones, okay? So somehow, those are the connections that probably, can also be referred and, of course, being used, let's suppose, by this particular software. So the purpose of Dijkstra, I'm sure you use Dijkstra very much, let's suppose, using your car, okay? So this is already a reference, so let's suppose, of a very typical special problem that it's been probably very much used on this. Another one is sometimes what we call the Kruskal minimum spanning tree. The minimum spanning tree, those are the two major algorithms that are known. One is Kruskal and another one is prime. But the purpose of the minimum spanning tree is a kind of a variation of the Dijkstra. So the minimum spanning tree here is I have a set of points and I want to know how can I connect to those points with the minimum cost. Okay, so this can be probably very important, let's suppose, for a company that has different types of sources, different types of branches, different types of warehouses. I want them connected with a private line, but I want to know, what are the minimum costs that I can do it. So once again, this is also a special problem. Let's go here for the Kruskal, could be also the other one. Okay, once again, like I told you, for illustration purpose, I have here kind of a small example about this. Okay, and I don't know why. Oh, this is, let's suppose, just a video about Kruskal. Okay, so somehow I also recurrent, let's suppose. And once again, if I want an example, there you go. So this is, let's suppose, a small example about the Kruskal theory. Okay. Once again, I always try to give a little bit about the context of that particular method or that particular, let's suppose, information, help. And in all of them, you have always, let's suppose, an example that certainly you can follow. Okay, so let me go back here again. So let me go here to Kruskal, opening this zip file. In fact, I have here two cases. One of them is about also from Brazil, and another one is also from Macau. So let's suppose, let me just select all these points. Okay, there you go. I'm doing the extraction. Let's suppose go back here to downloads. Okay, let me go back here to downloads. All right, and once again, let me just try to see, let's suppose, the example of Macau. Okay, so somehow kind of a land that somehow has kind of a lot of meaning for me. So once again, we have here, let's suppose, a small example. But once again, the purpose again and again. So imagine, let's suppose, I have, let's suppose, those 1, 2, 3, 4, 5, 6, 7 points. Okay, so these are somehow, let's suppose, landmarks of Macau. Okay, all of them. So let's suppose I want to take a route and I want to visit all of them. Okay, but I don't want to walk too much. So I want to know what is the best way for me to walk less in order to visit all of them. Okay, so that's a little bit about the purpose. So once again, this is where the minimum spanning tree can come along. This is, let's suppose, a text file that you can download it. Let's just probably FFU. So once again, I have 7 points. And these are the distance from point 1 to all the other ones, from point 2 to all the other ones, and so on and so on. As expected, the distance between the point and himself is always 0. So that's why we have this diagonal as a 0 value. Okay. So let's choose here the file. Okay, so once again, those are the points. So let me pick it up here, the file. Let me do here the upload. Okay, so I have here those particular points. So I have those nodes, node 0 to node 6. Okay, so these are the costs in order to move from node 0 to node 1, node 1 to node 0 to node 2, and so on on a very much table. And once again, these are, let's suppose, the result of this particular Kruskal algorithm. So we have to connect vertex 2 with vertex 3, vertex 3 with vertex 4, vertex 4 with vertex 5, vertex 0, vertex 1, vertex 0 with vertex 6, and then vertex 1 with vertex 6, 5. So if you do like this, these are, let's suppose, the minimum costs that somehow I should pay in order to connect all the points. Okay. And the total cost in this particular case are 35 units. Once again, the units could be anything that you need at something to use, okay? So most of the times it's very much associated to money, sometimes very much associated to effort, sometimes very much associated to human power, sometimes very much associated to time, sometimes associated also to distance, you know, so whatever it is, it's just a cost. And you wanted to minimize those costs that somehow all those points probably are very much intercorrelated, okay? We have also here the cluster. Once again, this is a method that somehow I have it here, but when you look at statistics, we have something called special and also another called a special or non-special. This one is non-special approach. I can use it, okay? So once again, what we're trying to do here is a kind of a dendrogram. So we're talking about clustering and we're also talking about hierarchical clustering, okay? If you still remember the clustering, most of the time we have k-means and we have hierarchical clustering. So somehow what you're trying to do here, hierarchical clustering, but somehow I'm just using, let's suppose, objects that are a special object or somehow it's a special location. So about those regions. Let's suppose that I'm studying, let's suppose, a variable, which is the quantity of water that rained last night on region number 1, region number 2, and so on and so on. So I want to try to figure out, can I figure out clusters, let's suppose, on those particular regions, okay, in terms of the quantity of water that was dropped last week. Again and again, you can do this, okay, but once again, remember that this kind of approach is not a very particular special statistics, because I'm just using the normal typical statistics in order to handle, let's suppose, information that somehow is geographical connected, but that's it, okay? But once again, you may find it here. I'm not going to all these kind of options, but once again, the Dijkstra, probably the elevation, the point buffering, and the prime minimum spanning tree, all of these are, I suppose, in terms of point analysis, very special, let's suppose, methods, okay? Point buffering, basically the concept of buffering. So if I have a point, let's suppose, if I'm located, let's suppose, in this particular case, I'm located at Yas Island. I want to know, let's suppose, how many, let's say, how many branches of a particular bank I have, let's suppose, 10 kilometers away from me. So this is sometimes what we call point buffering, you know. So it's an area that somehow surrounds the point that we are, all right? In the elevation grid mapping, let me just show you here, you know, I have also here. So somehow the elevation is just to tell you the concept of altitude. So many times, you know, we can, let's suppose, also present, let's suppose that the third dimension. So let's suppose that altitude somehow also can be an important factor in terms of space. Okay. And once again, let me just here extract this to the downloads directory. In fact, I have already this particular file. Okay. And let me just do a kind of a small example. On this particular example, I just did a function somehow that can represent, let's suppose, on a 3D. So let me see here. There you go. This is the file elevation. There you go. Upload. And once again, there you go. So we have the concept of X, we have the concept of Y, and we have also the concept of Z. Okay, so this is sometimes what we call elevation. All right. Now, in terms of special regression, I'm sure you heard already about the ordinary least squares for bivariate regression. So one variable in function of another one. I suppose I have one independent in function of one dependent one. We have also a variation of OLS multiple regression. So somehow one independent variable in function of several, one dependent variable in function of several independent variables. I'm sorry, one dependent variable in function of several independent variables. And if that particular data doesn't follow sometimes what is known as a normal Gaussian distribution, you know, you can always apply the Spearman rank correlation, which is sometimes known as non-parametric tests. So somehow those values that we have of the data are converted, let's suppose, in rankings, first, second, third, and then we're going to use, let's suppose, that ranking in order to also to do, let's suppose, regression. So the purpose of regression quite often is trying to see the correlations and how strong are the correlations between, let's suppose, one dependent variable in function of the other independent ones. And also very much particularly useful for let's suppose, forecast for provision, for try to for estimation. Most of the time, this is what the right word for this. What happens with all this is whatever it is the approach that you apply it over here, the major problem here is all of them are very much the typical conventional or statistics, so somehow respecting, let's suppose, the concept of, let's suppose, of independence of the facts. We also believe that, let's suppose, there will be no collinearity between those variables. We also believe that the correlation, in particular the errors correlation, are close to zero. Okay, but the problem here is that Mother Nature doesn't care very much about, let's suppose, the laws that somehow are set up by man. Okay, so the only method that I can consider here that are truly, let's suppose, under the special regression, so somehow where the space really matters, is what we call GWR, sometimes known as geographical weighted regression. Okay, so let me give you a small example on the GWR. Basically, what it means here is I'm doing a kind of OLS, but I only care about the samples that are located for the estimated point that I'm trying to do. Okay, and I'm also trying to respect very much a little bit about Tobler's law. So basically, if I'm trying to estimate, let's suppose, a specific point, I only want to know, let's suppose, the 10 points that are nearest to me. Okay, and on those 10 points, I'm going to give you more value, more weight for the ones that are closer to me than the ones that are far away. So somehow these are, let's suppose, the major conception of the GWR. All right. So let me try to choose here a file. In this moment, let's suppose I'm going to pick it up. I don't know. I did it already. An example. So let's pick it up this one. So this is about the state of Ohio, one of the major states of, back in America, and we're trying to see the lung cancer among men. So basically, this is, let's suppose, I'm going to do here already the upload. So I believe I have here, no, this is not what I want at this moment. Let me just check it. Downloads, I have here several downloads. Just give me a minute. There you go. So let me see here what we have on this particular data set. So we're talking about Ohio. So once again, one of the states of the 50 states of the US. Okay. And once again, this 50 state has around 80 counties. Okay, so this is, let's suppose, the map, let's suppose, of Ohio, and their, let's suppose, respective. So I believe this state is somewhere on the middle, more or less. Maybe I'm not saying the typical, let's suppose, gravity point of in terms of space of the US, but somewhere is more or less on the middle of the country. Okay. And if I'm going to look, I suppose, at the file, what I have here is lung cancer. These are real values. Okay, I believe this is from the 1990s. This data set. So I have here the location. Okay, so in every, let's suppose, in every county of this particular Ohio state, in fact, we have 88 counties, and we have 5 variables. So one of them is the location, X and Y. Okay, so somehow the latitude, the longitude. Okay, and then I have the number of lung cancers that exist on every, let's suppose, every county of this particular state. And then I'm trying to figure out, if just because the person is a male, is white, or if it's black, does it have any influences on that? Okay, so once again, I'm trying to figure out, let's suppose, if the color of the skin, somehow has something to do, let's suppose, with the number of lung cancers, let's suppose, under the male, let's suppose, society of this particular state. So once again, this is, let's suppose, the data that I have around here. So this is a little bit about what I'm trying to find. As you might see here, we have a lot of states, but definitely, probably this X and Y, the latitude and the longitude of each state, probably has also something to do with this. Can I, let's suppose, can space, somehow help, on the analysis, for lung cancers, not between, let's suppose, black and white men. Okay, so that's very much, the question that we ask. Okay, of course, if I don't put the X and Y, I will have the typical, let's say, multiple regression. So basically, I'm just trying to figure out, what is the model that somehow makes me lung cancer man a dependent variable of the two independent variables, in terms of man white and man black. All right. So once again, let me just do something like this. There you go. Minimize this. So there you go. So I have here, let's suppose the samples. I have 88 samples, I believe. There you go. These are the number of, let's suppose, of deaf people from males, let's suppose, deaf males that suffers from lung. And these are, let's suppose, the coordinates of each country. So once again, here is, if I include this information of the location of each country, also does this matter, for this particular problem? So that's most of the time what we have here. So according to the GWR, we have different types of functions in terms of the weights, because somehow what I want in terms of this Gaussian weight function, for instance, is the samples that somehow are closer, to the counter that I'm trying to do the estimate, are probably more important than the ones that are far away. So this is very much what I'm trying to see. So somehow the conventional average is about 49. So I'm putting here the convention 550. Okay, so let me just put it here. So this is somehow the radius. Okay, so all the samples that have, let's suppose, a distance that, let's suppose, less than 50 from the point that I'm trying to estimate, I want to know what's going on over there. If it is over 50, suppose that weight should be 0. So somehow I don't care, let's suppose all the counties that whose distance, let's suppose, is bigger. So in fact, my distance is 1.82. So let's suppose I'm going to consider, let's suppose, the distance of 2. All right. So once again, that's basically what I'm trying to say. All of this, are formulas. I'm not going very much into this. Okay, it's not to the purpose. Okay, it's just for you to start getting acquainted. How can I use this? So somehow GWR is a very good extension, I suppose, of the typical, OLS regression that we have. Of course, when you're talking about regression, we can also apply probably partial squares, PLS, sometimes WLS, weighted least squares, and also sometimes even using bootstrap, capabilities. Okay, but quite often, most of the times, OLS is being very much used, I suppose, by the majority of the researchers. So somehow, this GWR is a kind of an extension of that particular OLS. So once again, let me just take, let's suppose, this particular sample. So I have here sample number 2. This corresponds to a specific county of the Ohio state. These are the locations, okay? And the value we have, let's suppose, 39, let's suppose, depth of lungs inside of males for that particular year. So the number of men white is around 48,000, and the number of black males on this particular count is 6,316. Okay, so these are the betas. So once again, this is the beta 0, so sometimes known as the independent factor. Okay, so the beta 1 and the beta 2, somehow tells me, the strengths, that somehow is related, let's suppose, with the men white and also with the men black. Okay, so as you might see here, the relationship with the men black are stronger than let's suppose, with the men white. So just look at the values of the beta 0 and the beta 1 and the beta 2. So according, let's suppose, to the real value is 39. Okay, but GWR, using, let's suppose, this best estimator, somehow it calculated that the value should be 44. So somehow we have here, I suppose, a residual. So we have here an error associated to that. Okay, and then we have also here, let's suppose, another value which is called the local weighted RSS, and of course we want to know that value should be associated with this. So all of this, are as you might see here, all estimated points, they have a different betas. So let's suppose for sample 75, let's suppose county number 75. These are the betas associated with this. The value was 16. The system, let's suppose, estimated 70. Okay, so there's a small error. Okay, let's suppose if we go to another state, let's suppose sample number 76. The value was 157, but the system only certify or estimate only 140. And these are the different betas. So as you can see here, for every, let's suppose, for every sample, we have, let's suppose, different betas estimations associated to that, okay, which is certainly a different type of concept that definitely it didn't exist as opposed with the typical ordinary least squares. So what are the things that I can learn? So somehow these are the map of the 88 counties of Ohio, okay? We can see here by the size of the bubble where, let's suppose, the majority of the death by lung cancer on males, okay? And this is sometimes what we call, let's suppose, the estimation error. So the estimation error sometimes is positive, sometimes it's negative, and somehow should be somehow random distributed. Okay, as you can see here, it's not completely random distributed. We have here some kind of special correlation. So once again, we have here the reds, which I believe are positive, negative residuals, and the blue are positive residuals. So somehow positive residuals, somehow it just tells me that I estimate over. On the negative residuals, I estimate under the real value. Okay. As you might see here, it's not completely random. Okay. I have here some pockets, let's suppose, of residuals. Okay. So somehow it's not completely, as probably the laws of statistics should be. This is, let's suppose, the beta zeros. So somehow, basically the beta series, sometimes known as the GWR intercept value, is a constant value. Okay, so I can see here just by the default, that the highest values, I suppose, of sampling, let's suppose, if I'm not consider any other values, any other independent variables, we have higher values, I suppose, on the south and on the north. Okay, so that's basically what I can say about those beta zeros. But what really matters is this one. Okay, so somehow using GWR, I'm trying to figure out for beta 1, if you still remember, beta 1 is one of the factors that somehow is associated to the population Caucasians males that exist on those 88 states. So somehow we have here, let's suppose, the highest values is very much probably a little bit more on the east side, if I may call it. Okay. And somehow, I can see that the white males in terms of the east side are more stronger or more propense, to have, let's suppose, lung cancers than the ones that live, let's suppose, on the west side of Ohio State. That's a little bit what I can say. And it's funny because for the black people, it's exactly the reverse. Okay, so. If let's suppose if you are let's suppose a black male, probably you like to live, let's suppose, on the east side, and the white males probably going to live probably, like, say, on the west side of the county of Ohio. So this is what I can say right away, and certainly it's a kind of intriguing, but this is what the data can tell us. Why is this? We don't know. Okay, at least based on this particular information, I don't know. But these are probably important clues, okay? Because I never thought about this, okay? So this data is real, and using, let's suppose, this approach, this is what I can say, okay? So if I was, let's suppose, and I am, let's suppose, a Caucasian male, probably if I'm going to live on Ohio and I don't want to suffer very much with the probability of lung cancer, probably I'm going to live on these particular states, okay? So somehow, let's suppose, on the east side, let's suppose on my left side. If I'm a black male, probably I'd like to live on my right side of the, I suppose, of the Ohio State. So why is this? I don't know. But GWR can tell you already this. So these are certainly probably some kind of conclusions that definitely GWR really can give us. That definitely other methods or other approaches are not able to do it. Then we have also here a little bit about event analysis. Okay, so event analysis is very much associated like the concept events. Let's suppose we have an earthquake, we have an hurricane, we have a desert storm. Okay, all of these are events. So all of these, are, let's suppose, things that happens, somehow in space. Okay. So binomial distribution, geometric distribution, and Poisson distribution, all of these, are, let's suppose, distribution that you probably have learned it, when you study, let's suppose, statistics, and particularly, let's suppose, distributions that somehow they have only very specific values. Okay, so let's suppose on the binomial distribution, let's suppose the output, let's suppose of that event is true or false, 0 or 1, success or not success. Okay, so somehow these are very much associated with this. Whatever it is, this kind of distribution, all of these are also no special, let's suppose, statistics, because somehow the capability to incorporate, let's suppose, the information of space is not associated with this. Okay, so it's very much, what we have here. I'm not going very much into to these ones. Okay, so once again, because probably you already learned it, but you can always apply it. So binomial distribution is very much associated to events that somehow, let's suppose, there was a burglar or there was no burglar on this house. Okay, so somehow it's very much a binomial distribution. The geometric distribution, most of the times we want to know what is the probability of the first success. Okay, so most of the times I'm just looking for the first time that you'll have. Okay, so that's very much associated to the geometric distribution. And the Poisson distribution most of the times is based on the average of events. Okay, so let's suppose in the Philippines, in average we have around 8 typhoons per year. So what is the probability to have, let's suppose, 10 typhoons? What is the probability to have only 5 typhoons on 2022? Okay, so somehow this is very much associated with the Poisson distribution. So whatever it is, binomial, geometric, and Poisson distribution are not related, or at least it doesn't underline, let's suppose, the concept of geographic information system. We are just applying, let's suppose, geographical data to non, let's suppose, special statistical methods. Okay, so that's basically what we're trying to do. The index of nodes and mental, it's a little bit probably more complicated. I'm just going to try to avoid, but somehow try to make the relationship between space and time. Okay, so somehow this particular index is maybe sometimes can be used particularly by the policeman department. So somehow in terms of softwares, when we have, let's suppose, murders in terms of time, in terms of space, this particular nox and mental at least can give us, let's suppose, probably the best estimation in terms of the approach itself. The moving average, it's a method which is also very easy, but somehow at least it's also in terms of special. Okay, and so somehow let me just click it here. Let's suppose this example in order to use this. Once again, it's very much also associated to events. Okay, so let me try to see here what do I have here, and let's suppose. Let's consider here, let's suppose, the city of Toronto back in Canada. Okay, so once again, these are just fake information. Okay, it's not real. But the purpose of this is just try to figure out, what is the moving average. So the moving average, although it's very simple, at least it's a special, let's suppose, function that we really can use it, let's suppose, inside of the geographic information system. So let me just see it here. There you go. So let's suppose I have here, let's suppose, a Toronto map. Okay, let me just show it here. And somehow Toronto is it's a beautiful city, let's suppose, on the state of Ontario. And imagine, let's suppose, I have here 1, 2, 3. All of these are events, let's suppose, of burglars. Okay, that it happens, I suppose, on this kind of sequence and also in these specific locations. Okay, so I have here, let's suppose, one burglar, then I have the second burglar here, then I have the third burglar here, 4, 6, and somehow the police is trying to figure out, okay, where do you think will be the next one? Okay, so this is somehow what the moving average is going to try to tell us. Okay, of course, it's not a fortune teller. This doesn't mean that the burglar is going to be there, but at least according, let's suppose, to the event, let's try to see, what the software tells us. So the moving average basically is going to grab, I suppose, let me put it here, Toronto owns burglars, probably this. There you go. Let me see if it works on this one. Upload. Okay, there you go. So there you go. So all of these are the different types of events that you may find it, and it seems like probably, let's suppose the next burglar will be probably close to event number 6. Okay, so probably, according to this approach, okay, let me just show it here, probably, should be close to this music hall. Okay, so that's what I can say based on this. All right, so, but once again, it's a very simple method, but somehow it's incorporated, this special component and also this time component. Okay, so somehow there's also a time, or let's suppose, a situation associated to that. All right. So this is what I have here, let's suppose, for in terms of the functions. Okay, so probably as much more to say. I'm trying to protect all of you, let's suppose, from the computation side. It's not the purpose of this. I'm also not trying to talk very much about, let's suppose, the technology that somehow they are used behind. So everything is this moment is completely protected, from that different type of perspective. Like also I mentioned, once again, this second menu is very much associated more as a process. Okay, so once again, it's very much associated to an area which is called interpolation. Okay, so interpolation, it just means I have samples, and then I want to estimate based on those particular samples, how it's going to look like, let's suppose the whole map. So there you go. Let me go back here. I'm going to pick it up one sample. So this is a true sample. It comes from a book, probably one of the most famous books of geostatistics, from Clayton Dutch and the journal. And once again, it's part of a software that they created called GSLib. Okay, this GSLib is open, it's for free, everybody can use it. And once again, if I click it here, I have here my data set, okay? And somehow this has to do with pollution, let's suppose, that of a very particular lake. I don't know where is this lake, probably if you go to the book itself, probably you may find it. Okay, let me just copy this, okay? But we're talking about pollution, okay? So once again, we have, let's suppose, a lake. We have in terms of the lake, the location, and then we have, let's suppose, how many ppms, let's suppose, parts per million, in terms of, a very specific pollutant, that probably they may find that, let's suppose, on this particular data set. So once again, let me just try to choose this. I believe this data set is around 100 samples, something like this. Let me just see it back here. There you go, data set. There you go. So this is my data set. Okay, let me just upload it. Okay, and we're going to use this data set for all this process around. So this is my, let's suppose, input observation. So I have here, as you might see, we have around 140 samples. Okay, these are the locations. Okay, and once again, this is, I believe, real data. So once again, this is, I believe, probably arsenic, or maybe lead, somehow, a pollutant, let's suppose, chemical product that probably they find it, let's suppose, somewhere inland or somewhere on the water. So we have low values, okay, but we have also very high values. So somehow what we're looking for here is, if I know the samples, can I estimate the whole area? Okay, most of the time that's what happens, most of the times when you look, let's suppose, at the weather, when you see those beautiful maps, most of the times it's based on sampling. Okay, most of the times there is no samples in every place, in every corner. It's not possible to do that. All right, so it's based on those particular samples, and that definitely, on those particular samples, we try to do estimation. So sometimes this is the problem of interpolation. So after reading those values, let me try to apply some univariate statistics. So once again, all of these are values and a kind of measures that somehow you were already learned. And as you might see here, this is a very high positive skew distribution. So it doesn't follow for sure the normal or the beautiful Gaussian distribution at all. So definitely even if I want to apply, let's suppose, this particular statistics, these statistics are very nice, but if they follow a normal distribution, okay, we can do it. But if you look at, let's suppose, at the skewness index, it's 4.45. It's very, very high. So even if you look here at the histogram, or let's suppose the box plot, it should be somewhere. Let's suppose here, this box plot should be somewhere here on the middle, not, let's suppose, on my left side. All right. So these are the distributions. Once again, we have here also some kind of measures, sometimes known as the nearest neighborhood for the clustering purpose. And these are the values that we got. So as you might see here, we have a certain region that somehow we have very high values. Okay, the majority seems a little bit more low, and so on and so on. So the question here is, how can I estimate all this area? Okay, so this area could be small, maybe just a small town, but sometimes could be a big lake. And we're talking about a big lake, maybe it could be 100, 500 kilometers away. Okay, so the question here is because we don't have sometimes the financial means in order to make samples of the way that we want it. Okay, so somehow this is probably where, let's suppose, these methods can come along. We have also here different types of nearest neighborhood analysis. So this is also very much statistics and special statistics approaches based on the sampling or locations itself. Okay, so all of this are, let's suppose, things that certainly we really can do it on this. So once again, this is part of the GSLib. Once again, as you might see, this is an executable file. I believe this is import 90. And once again, there's some kind of calculations for that. Okay, so we need to know this for something that we're going to do later on. We have then all these options. Okay, so let's suppose if I want to do a 2D, 3D data set. So once again, this is, let's suppose, the 3D option. If I want to see the 2D, I can figure out, let's suppose, the samples divided for the 3 groups. Okay, so somehow the ones that have low values, which is the dot blue, I have the diamond red on the middle, and then the ones that are yellow are, let's suppose, the highest values. Okay, and in fact, we have, let's suppose, the samples itself. So it start telling me very much, where are, let's suppose, the pockets that probably I should be aware of this. And definitely know this can be important in terms of pollution. So what are the areas that probably I should take more in attention in order to clean it, let's suppose, for a clean operation, okay? If this is a huge area, remember, I don't have the means in order to make all of this, okay? So somehow all of this can probably sometimes create problems in terms of also in terms of environmental problems itself. I don't know if you notice, we have also the t-test and FT test. So somehow it's also possible, of course, to apply. I can, let's suppose, divide these samples, let's suppose, in different areas and try to compare, let's suppose, one area with another area. Okay. So once again, there's a lot of options around. Okay, that's very much. This is the x-axis profile scatter plot. So basically, I'm trying to see here, let's suppose, from the coordinate x, how the samples they arise in terms of the x coordinates. And I have also another option, which is, I suppose, on the y profile scatter plot. So once again, there you go. All right, that's very much what I have around here. Now, like I mentioned, spatial dot correlation is very important, particularly for spatial calculation, because we want to know how the data are correlated among themselves. Because by default, Mother Nature, the spatial dot correlation is around 0.25, 0.3. So this spatial dot correlation is a measure that can vary between -1 and +1. Okay. If it is -1 or close or negative, we call negative spatial dot correlation, and if it is positive, it's what we call positive autocorrelation. When the spatial autocorrelation is 0, so basically we are moving, let's suppose, under the typical statistics. Okay, so somehow the samples are independent of each other. So somehow we are living on a random world. Fortunately, the world is not completely random. Okay, so there's always this kind of spatial autocorrelation, and this is good. Okay, definitely this is good, because if we're living on a, let's suppose, on a spatial autocorrelation opposed to 0, quite often, all the events that we have are completely random, and we know it's not. Okay, so definitely the majority of the cases, spatial calculation on this particular scale, most of the times around plus 0.25, 0.3, sometimes 0.4. Okay, so most of the time that's what we have around here. Now, let's put here the data class mapping. So somehow it's also divided, let's suppose, those mappings in the 5 different types of classes. So once again, I can already figure out, certain types of areas that are very propensive, let's suppose, for high values. Then I have here small pockets. It seems like this area that are represented, let's suppose, by this light pink, are the ones that the levels of pollution, are quite low. Okay, so once again, So in order to measure, let's suppose, this special alpha correlation, we have several measures. Okay, one of them is the variogram. Okay, so the variogram somehow is a formula, is a, let's suppose, a function that somehow quantifies, the special alpha correlation in terms of space. Okay, so it's quite normal that the variogram, somehow it's very much, it's the inverse of the correlogram. Okay, so basically it's expected, let's suppose, that samples that are very close, the value of the variogram are close to zero. But for bigger difference of a different distance, those let's suppose measures, the value of the variogram are very high. So somehow this is most of the times what are going to find in terms of the variogram. But once again, it's just a tool, it's just a function that measures, the level of special population in terms of space. Okay. So we have here several values. Okay. In order to calculate this variogram, we need to calculate all these parameters. Once again, I'm not going very much into this as well. Okay, I'm trying to protect you from this. So the leg distance, I will put it, let's suppose 2.4 because somehow it's a little bit bigger than the mean distance. The number of legs, I'm going to say I want around 10. The tolerance angle will be 23 because somehow these samples are kind of random. Let's move put the leg tolerance about 2, the bandwidth also about 2. And let's see about the contiguity. So the contiguity just tells me very much sometimes what we call an isotropy. So an isotropy just tells me, certain, let's suppose, events, some special movement on the planet Earth. Most of the times they have a direction. Okay, so somehow this is what we call, let's suppose, an isometry, or sometimes known as the contiguity direction. So let me put here, let's suppose, this contiguity direction. So something like this, probably I'll put it here, let's suppose, around maybe 45 degrees. Okay, so once again, this is just probably a starting value point. Pressing for the variability general computation. There you go. So some values were calculated. It doesn't matter how was it. Okay, but somehow what I'm trying to figure out on this variogram fitness here is, what is the formula that somehow tells me, how special population varies for this particular case study that I'm trying to do? So we have different types of measures. One of them is the colorogram, another one is the methogram, another one is the relative variogram, another one is the pairwise relative variogram, and another one is simply the variogram itself. Okay, so all of this somehow tells me a little bit about, in general lines, how can I, let's suppose, measure, let's suppose, this variogram. By the colorogram, I can see already, let's suppose, when the distance is probably around 7, 8, it seems like after that, the colorogram is close to 0. So basically, it just tells me that all the samples that are bigger than 7 or 8, those samples, it doesn't matter. Okay, so right now I start already having an idea. What are the samples that really matters for the one that I'm trying to estimate? So the ones that I really want are less or equal than 7, 8. Okay, that's basically what I can say here. When I'm looking at the methogram, probably this value comes to 10 because once again, every form has a different approach. If I'm going for the generative relative, it's also around 10, and also this one is around 10. So probably I'm expecting that the 10 units, it's somehow the distance that's going to tells me a kind of a cutoff value. If I'm doing an estimation, I just wanted the samples that's going to contribute for that estimation that are below 10 units. If it is over 10 units, I don't care. Okay, so somehow this is very much a little bit what I can say right now. So somehow this is the variogram. So the variogram, once again, we have 4 major distance. I said, I don't know if you noticed one of the previous parameters that my level of contiguity seems like it's around 45 degrees. So basically it calculates for 45, calculates for 90, calculates for 135, and also calculates for 180. Okay, so try to see what's going on around here. Now the problem is of the variograms sometimes here is the variability of the values, because somehow these are formulas, and then also sometimes can create some kind of erratic. So somehow I prefer sometimes the previous measures for me to tell you a little bit about the story about what's going on here. So let me start considering, let's suppose, based on this, this is the only directional diagram. I can also do some kind of interactivity fitness if I want it. So let me just try to put here, the major range will be 10. Now what will be the minor range? Okay, yeah, it seems like the minor range should be probably a distance less than 10. Okay, also can be 10. Okay. So if I put here, let's suppose 10 around here, let's suppose on 90 degrees, probably my value is probably around 9, maybe 8. Okay, so let me consider here about it. So once again, the problem of all this very much based on experience. Of course, if I want to do probably a better variogram in terms of the parameters, probably I need to redo this again. I need to recalculate, several times. And sometimes you spend several hours in order to figure out what are the best parameters for this equation, because somehow we don't have here a formula for this. Okay, so somehow it's very much based on experience. It's very much on trial and error. This is most of the time what the book says in order to figure out those parameters. Now the negative effect, somehow I have here a kind of a negative effect. So if you look, the negative effect probably is around 60, I have 120, so we're talking about 50%. Here I have 20 of 60, we're talking about 30%. This one is a very bad, let's suppose, omni diagram. So let's suppose the negative effect, I will consider, let's suppose, 40, okay? And the seal, I'm going to consider probably around, I don't know, 80, okay? So let's put it to this. So it just tells me that the model I will consider probably spherical, and I'm going to try to disable these parameters, and that's okay. So once again, that's I'm not going again. There's so much theory behind all these kind of parameters. Okay, so there could be a lot of discussions and everything. What really matters for me here is I create a formula. Let's suppose a spherical formula, and those particular parameters are not known as the negative factor, the seal. And also the range and the minor range, and I suppose the anisotropy factor that somehow tells me or helps me in order to quantify special occurrence. That's what really matters for me. All right. Now I have here also some other ones. Moran I, most of the times it's also another. In fact, we have Moran I, we have Gary C, we have Lisa. All of these are different types of approaches in order to calculate, let's suppose, special occurrence. So all of them, try to figure out in terms of modern age, where's the autocorrelation of the phenomenon that I'm trying to study. Okay, this is an approach that somehow I did here some kind of changes. So more than I, so as you can see here, when the distance is close to 0, the value is also close to 0. Okay, so somehow this tells me or certifies me that what I consider the major range as 10 is probably a good distance. Okay, so that's very much a little bit what I can say. This is the formula of the Moran I. It doesn't matter very much. Also here for the purpose. Let me do here the Moran location scatter plot. So once again, try to figure out here patterns. So high, low, and high, low. So somehow here I'm looking for outliers. So somehow low values surrounded by high values, and here is high values surrounded by low values. And here I'm looking for patterns, so high patterns and low patterns. So somehow I'm trying to figure out, and then of course, this cutoff value I can create as occlusive areas sometimes from 5, 0, 10, 15%. So let me just consider the default values. So somehow these are the samples. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay. And once again, because this is somehow off map, sometimes I believe this is called the best way. So once again, all of these are, let's suppose I have, let's suppose you have 2 major pockets, maybe 3 major pockets, okay, of high positive values. So this is what we consider quadrant 1. I have this one, and this one. This is, let's suppose, the areas of the lake that it seems like the samples are very, let's suppose, low. Okay, so this. So definitely, if you want to take a swimming pool, you better probably to swim around here. Okay, not on those areas. Okay, because of high levels of pollution. And then we have here, let's suppose, the negative outliers and the positive outliers. Okay, so somehow once again, those are the things that at least I can show you here, let's suppose, according to this particular map, all right? And again, I have also something called, this is also one of the measures that somehow I created, or I'm sorry, I'm just putting here. On this one, I did kind of this enhancement for the modern. I believe that this kind of visualization is better than the default one, which was the previous version. This modern variance scatter plot somehow it's also based on a modern, but it's very much based on the concept of variability. So I want to know where is the variability of the values inside of the map. Okay, so that's very much a little bit what we're going to have here. So press C for further general computation. Okay, and there you go. So somehow I can see here that all these areas, somehow are the variability, somehow are stable areas. But we have here, let's suppose, I have the region represented by the black. I don't think there is any black around here. But we have here outliers under this area, and then we have also median variability on this one. So these samples here consider, let's suppose, according to this approach, some kind of variability of the values. Okay, so somehow high, sometimes low, because variability always means for us uncertainty. Okay, in terms of our own estimation. So all of these are measures that somehow are correlated with how can I measure, let's suppose, in terms of quantitative approach, special correlation. And now finally we're going to reach, the interpolation. So this, and this, all of this has to do with the interpolation. So I wanted to figure out how does this lake looks like in terms of population, in terms of, let's suppose, estimation, okay? We have different types of approaches. So we have the stochastic, sometimes known as probabilistic interpolation. We have the deterministic interpolation, and we have something called simulation, okay? So what is the difference between simulation and those interpolation approaches? Well, interpolation always means to go for the average. So every time that we do an interpolation, either if it is stochastic or deterministic, the map that we're going to get, is always very much sometimes close to the average. Okay, so somehow the variability in terms of interpolation is always lost. Okay, on the simulation, it doesn't happen. Okay, on the simulation, most of the times that the variability that we can find, let's suppose, on the initial, like the sample, somehow is reflected, let's suppose, on the map that I'm trying to do on the sequence. That's why we call simulation. Okay, so it's two different types of purpose. Interpolation, most of the times, what we consider the error is smaller than on the simulation, but the simulation, on the other hand, has more variability, so it's probably more real. Okay, so most of the time, that's the big difference between interpolation and simulation. And then inside of the interpolation, we have the stochastic. So somehow it's possible to make an interpolation, but it's also possible to calculate how sure you are about your interpolation. So what is your level of certainty or uncertainty? On the deterministic interpolation, it's not. We just get to the values and that's it. We don't know how sure you are. Okay, so basically we don't have any kind of measure, of the level of confidence associated with your own interpolation itself. So let's try to do it here. Let's suppose ordinary kriging. Okay, so this is one of the methods that was set up by a French geostatistician. Okay, I don't remember now his name. I'm going to say that I don't trust, let's suppose, my sampling. So most of the times I'm going to say every time I sample, I have a 10% error on that particular measure. So that's basically what I'm trying to say on the measure error. All right. So once again, I'm not going very much to this. So these are just small calculations that somehow the software needs to be done. Okay, because what I want in a moment is to calculate how does this map looks like. So based on those samples, according to ordinary with my negative fact, which is around 50% of the values, these are, let's suppose, how my map is going to look like. Okay, so that's my interpolation. Is this a good interpolation? I have my doubts because I don't know if you notice my highest value is 23. But if you look at the samples, I have samples the values are higher than that one. Okay, so once again, this is the major problem of interpolation. Most of the times, we get, let's suppose, small errors. Okay, if we calculate, let's suppose, residual errors most of the time in terms of interpolation are smaller than the simulation. But once again, we lose very much about the variability. So once again, Look at this one. So with no negative factor, the values are already a little bit different. The other one was around 27 or 25. Here the value reached around 50. Okay, so all of this, can tell you very much a little bit about, let's suppose, possible maps of estimations of how probably that map looks forward. In all of this, in terms of kriging, we have also some what we call the kriging variance. The kriging variance just tells me, because the variance always somehow translates me how certain you are. If you have a high variance, it means very uncertainty. If you have low variance, it means you have a lot of certainty about what you're trying to do. So what I can say here by this ordinary kriging variance, it seems like this area, let's suppose somewhere here, let's suppose on the bottom, we have a lot of uncertainty. So basically, one of the questions that I could do here at this moment, if I have probably more money to do some more sampling, I will put it here. I will try to put it on the red, on the orange, and also on the yellow zones. Okay, I will not put samples where I have blue zones. Okay, so that's already. Now the problem of this measure that I have over here is only special dependent. So somehow, basically what it means here is it tells me where do I have samples and where I don't have samples. Okay, so on this yellow, I need more samples. On this red, I don't have samples at all. So that's basically what it means. Okay, so somehow this kind of uncertainty is also special dependent. Okay, but it doesn't depend also on the variability, also on the values, because somehow the uncertainty is measured by two major dimensions. One of them definitely is the space, which is somehow captured, let's suppose, by this ordinary kriging variance. But definitely, it's not, let's suppose, captured by the variability of the values. Okay, so somehow this is called not a very good measure, but nevertheless, it's better than nothing. All right. And then we have also another version of the ordinary kriging, which is called the NASA. So once again, as you can see here, another version. So small difference, of course, you may find it in terms of the interpolation itself. Okay. I can also do some kind of cross-validation. So the cross-validation basically just a method that I'm going to take that sample, and then I'm going to do an estimation on that sample and try to make the difference. Okay. So once again, it seems like according to the three models that I did it, once again, according to the cross-validation, these are, let's suppose, the methods that somehow get, let's suppose, better approaches. Okay, so some of them, the samples were best estimated by model 1, other ones by model 2, and other ones by model 3. All right, so that's a little bit what I can say. So somehow this just tells me those three approaches that I do in terms of ordinary kriging, none of them is superior to one or the other one. So sometimes in different types of regions, this one is better, the other one is better, and so on and so on. These are the ordinary kriging difference. So this is between model 1 and model 2, model 1 and model 3, and model 2 and model 3. So somehow this is what we have. We have less of a difference. So as you might see here, let's suppose model 2 and model 3, this has the biggest difference, okay? And it's a very negative one. So basically model 3 most of the times calculate higher values than the model 2, okay? Now we have also another possibility, which is kriging with trend. So somehow I can apply a trend and then I can apply kriging over the residual of those trends. I'm not going to do that. And another possibility is indicator kriging. Okay, so indicator kriging is also very much associated, let's suppose, to distributions of those particular samples. Okay, so that's one of the things that you also figure out. Okay, there's a lot of things also going on here. Definitely, this is probably one of the areas that somehow probably I like it most. But I'm not going very much into this because once again, it's just we're going to talk very much about cumulative, let's suppose, distributions, functions, and also entropy of Shannon. I don't know, the types of estimations, or this kind of free type estimations, a kind of similarity of ordinary kriging with trend, but there's a lot of things going on around. Okay, even morphological geostatistics set it up, let's suppose, by one of the both Professor Gubert and also Professor Nilkar Soares from Institute of Technology in Lisbon. So whatsoever, there's also a lot of things around. Okay, so once again, for me, just for you to have an idea that there's a lot in terms of estimation, in terms of space, because every time that you look, most of the times at the weather, let's suppose, for instance, which is quite common every day, you like to look at the charts. Believe me, those data is always estimation. Okay, so somehow we're talking about interpolations. Now, the problem of interpolation, like I mentioned, you always smooth the facts. Okay, so by smoothing, we're going to lose very much the variability of the facts. So somehow this is where simulation can come along. So simulation, here I'm talking about a simulation, let's suppose a conditional simulation. But once again, I don't know if you noticed, this is let's suppose a study, I believe, accomplished back in Brazil. And basically, this simulation number 30, 68, 176, and 214. So this is about the emission in terms of soil of dioxide of carbon. Okay, this is the measures. Okay, and once again, as you might see here, these simulations always gives interpolation, I suppose, with different types of variability associated with this. When you're doing the heat type or the ordinary kriging, I don't know if you notice, we lose very much that variability. Okay, so this is the minimum values of all of them. This is the maximum values and the standard deviation associated with this. And the standard deviation is always important because this tells me, how much certain you are, let's suppose, about, or let's suppose, your own estimation. So the red ones, it always tells me that, I'm very uncertain about those areas. But the green ones, it seems like I'm pretty certain about, let's suppose, of the value that can be estimated for this particular emission of dioxide of carbon. Okay, so once again, probably it seems like a very important factor, let's suppose, for the agriculture, okay, purpose. So there you go. I'm going to press here for further geocomputation using still our home data, okay. And we're going to generate it here 10 possibilities of possible maps. Okay, so this is why we call, let's suppose, simulation. So let me try to see here, let's suppose this particular version. So all of these are possibilities of outputs with the same probability, let's suppose, of that particular label. So it could be something like this, could be also something like this, or something like this, or something like that. Okay. What really matters here is we have here different types of variabilities. So somehow, is this one or this one? We don't know. Okay, we just can't tell that the probability to be one or another is exactly the same. But one thing that's for sure, the variability of the data is exactly the same one of the initial data set. And this is a property that certainly it doesn't happen, let's suppose, for the estimation. On the estimation, the values are always much less than 57. Okay. So basically, although the arrow is less, okay, but we'll also lose very much the variability. So basically, there's also something wrong with this. Okay, so somehow this is where simulation. So if I'm looking at the statistics, okay, we call this realization. On realization number one, I don't know if you know this, the maximum is 58 and the minimum is this. If you look at this one, the values, always, try to somehow to have the same kind of let's suppose descriptive statistics itself, so that there's not much difference between one or another. All right, so definitely there is difference, but definitely the realizations itself are definitely certainly very important to this. Here's let's suppose a 3D perspective of this estimation. Okay, so maybe it could be something like this, maybe it could be something like this. Okay. So all of them, are different possibilities of models of how the real estimation is. Okay, and under this simulation, we can also calculate here let's suppose the mapping tool. So once again, what I have here, once again, this is let's suppose a conditional sequential simulation. So this is one. This could be another one. So based on the 10 realizations, okay. The top left, upper right there, shows the heat type average estimate of the minimum, maximum, extreme behavior of discussion. So here we're talking about the minimum values. This could be the maximum values that I may find. Okay, so I grab, let's suppose, those 10 previous simulations. I grab the minimum of each point, and I calculated the average of that minimum. And here I went to, let's suppose, to the maximum of each point, and I calculated the average of each point. So that's the big difference between one and another. So somehow, the values in reality, somehow could vary between this map that I have over here and this map that I can over here. Okay, so as you can see here, this is much more darker. Okay, because somehow, these values, let's suppose, are very much closer, let's suppose, to the bottom values by itself. And here we have what we call the standard deviation. So this is probably certainly something, somehow this is a standard deviation for each point, based on the 10 previous realizations. Okay, so this just tells me, let's suppose, on these areas of red, the variability of my simulations are very high. On this blue or dark blue, it just tells me that the variation of those particular areas are very small. So that's basically what it means. Okay. So definitely, this is an important map, particularly standard deviation for me is the most important one in terms of simulations, because it tells me, how much the data can vary on specific areas. Okay, and this tells me right away also very much about uncertainty. Okay, so if you ask me once again, what is the area that I am more uncertain? Certainly it's the red ones. Okay, so what should we do? Okay, maybe one of the things that if you want to improve your results, try to put in more samples. Okay, so somehow try to figure out, if this red will become more blue. Okay, but somehow I have the feeling here probably about uncertainty, and I know how to measure them. So I have an idea a little bit about what's going on. So let's suppose let's suppose the threshold. Let's put the 3. I don't know. Maybe 3 is, let's suppose, the number of ppm that somehow probably I should put, let's suppose, to do the cleaning or not. Maybe this is a decision-making process. And there you go. So I have here, let's suppose, the probability, let's suppose, on my left side of the values that are over, let's suppose, 3 ppm. And on my right side, these are, let's suppose, the probability that the values are less than 3.0 ppm. So somehow, the areas that definitely are very low values, the probability that are lower than 3.0 is around 98%, so which makes completely sense. Somehow one is the reverse of the other one. So I don't know if you notice, that's very much typical this. All right. So once again, it's very important, this kind of concept of stochastic, because it really can tell us very much, how sure you are about the things. Okay. Then we have also very much the conditional indicator, which is the variant of the conditional quotient. Okay, and somehow this is also very much based, I suppose, on this indicator kriging. Most of the time, this conditional simulation is because indicator kriging somehow it splits the values from zeros to ones. Okay, so somehow that's the purpose. But let's move on with this. Once again, we have deterministic interpolation. So these were the first approaches that probably the humans has always to do it. Okay, so on this particular case, we have simply let's suppose the interpolation, but there is no realization, there is no concept of how sure you are about it. So this is what we call the first order polynomial or linear trend surface. Okay, let me just try to show here the second order polynomial square trend phase. So somehow this is sometimes good for us to have an idea as a trend. Okay, so somehow that's probably the only purpose of this, but no one uses this in order to calculate interpolation. Other approaches, the multi-quadratic. Okay, let's put it here. Let's put the 0.1. And this is also another, I suppose, global multi-quadratic radial basis functions. Quite often, also very much deterministic. Okay, so according to this approach, this is, I suppose, the estimation, I suppose, of the pollution levels on this particular data set. Okay, so once again, all of them are inverse multi-quadratic. Okay, let's put also 0.1. Let me put it like this. So once again, of course, in terms of algorithm, there are differences. So as you can see here, here the value is only 14. So definitely no, this is definitely not probably a good interpolation approach with this parameter. We have also other ones, inverse distance. Okay, so once again, very much typical. Okay, so The facility of this kind of approach as a first way is for us to have an idea how it's going to look like. And in terms of computation, it's very easy, the computation of this. So somehow it's very much straightforward. Okay, once again, you don't have to set it up any special calculation measures in order to calculate this. The nearest neighborhood, so basically the value of a sample is based on who's my neighbor. Okay, so once again, and then I will get, I suppose, a sample, I suppose, for the unsampled locations. Okay. And we have also here the Voronoi and Delaunay, but it's not working because this approach somehow is based on Java applet. So once again, the Java applet should be on, but again and again, this only works, I believe, only for Internet Explorer. Okay, that's this. I did already that experience. So once again, and so that's a little bit about this. I hope somehow it brights you a little bit about this particular software, about the possibilities of using geographical data that sometimes is available on your own studies, and try to include, let's suppose, that particular data, because when you have the location and you have also the time, this is data. Okay, the question here is, how can I extract information for that particular data? Okay, so that's the problem. So most of the time, if you look back, I suppose, at your records of your history in terms of the high school, in terms of university, the primary school, secondary school, you never approach this. Okay, even when I look, I suppose, at the geography classes, most of the time it's very much descriptive. Okay, so we study, let's suppose, the rivers, we study the mountains, we study the cycle of the water, we study a little bit about the planets, about the universe. Okay, but it's very much descriptive. Okay. And this approach is a little bit more inferential. So I'm trying to make conclusions about things. Okay, it's not only to describe things. All right, and I'm trying to make correlations, and I'm trying to analyze things in a different perspective. Okay, so all of these are a set of algorithms that they really exist already at this moment. And I believe at this moment, geography, somehow, because geography is the science that somehow really cares about the where question. Okay, when you're talking about the where, you're talking about the geography. Okay, so somehow this is where, let's suppose, this particular science should move on and try to grab, let's suppose, new methods, new approaches in order to figure out, let's suppose, different types of problems that somehow space is important. We are living the coronavirus, as you know, the whole world knows this kind of pandemic. And it's funny, I saw already several studies about, the coronavirus, different types of patterns, different types of vaccines and everything. But I never saw very much also the special component being treated, because somehow this is the era of epidemiology. So epidemiology somehow is a spread of diseases in terms of space. And definitely geographic information system has something to do with this. All right, I hope you like it. I hope somehow you enjoy it, at least just to open a little bit your doors in terms of this kind of new quantitative geography. And once again, if you have any questions or anything, please feel free to shoot. And if not, I don't know, maybe you just can email me if you feel free to go. And if not, I wish you the very best, and definitely you have my complete respect also for being here and for listening to this. I'm just feel sorry I'm not on a face-to-face environment. I'm not even on a mask-to-mask environment. I've been already 2 times in Greece, and it's a lovely country. If you are there, please just enjoy it. It's a beautiful time also of the year to be there. And somehow it was in Greece that science started. Okay, so somehow it's also, in fact, math, everything starts over there. And so definitely, somehow geography also owes very much to the Greek ancestors people. Okay. All right. Thank you very much. Catch you later, alligators, and take care. Take care of you. Bye-bye. Thank you.